So today, we're going to take a look at it. We're going to take a look at what is known as an enthalpy diagram, and then we will also look at what is known as the collision model. So those are the two things we'll take a look at. So the first thing we're going to talk about, we're going to talk about chemical reactions. I'm going to talk about chemical reactions needing energy. And this is one of the things that Savitri Arrhenius, that you're going to see in the notes in 1 second, kind of figured out. He figured out that when it comes to chemical reactions, that they need a little bit of energy, a little bit of push here to get those things to actually take place. Give you a good example. If we think about something such as our Bunsen burner here. So here's my Bunsen burner. Once again, another one of my artistic skills here. Got a little tube feed into this thing right here. Feeding that tube, we got not CO2, we got CH4, methane. So the methane gas is going to kind of come through this tube here. It's going to come out and it's going to, of course, mix with the air. So I got O2 out here as well. What I know for a fact is if I just turn that methane on and it just kind of goes out here, the classroom is going to start to smell like methane. You're going to smell that odor of the methane gas in this case. There will be no reaction. If I want the reaction to initiate itself, I gotta give it something. What do we give it to get that thing to go? We use something. At Bunsen burner, what do we use to get it to go? Heat. We use the heat. And that heat comes from the little spark that we have there. That little bit of spark is the little bit of energy, that little push that this thing needs to initiate the reaction. And what Savitri Arrhenius once again realizes that, hey, every reaction requires some minimum amount of energy, some little bit of push that it needs in order for the reaction to actually proceed. And the reason why we need these energy is we need this energy to break the bonds. Bonds have to be broken. Once the bonds are broken, the atoms can go and rearrange themselves and produce, in this case, some new compound. But you gotta break the bonds in this case. And this leads us to this concept known as the activation energy. And if you look at it, we abbreviate activation energy with a capital E for the energy portion, because that's all it is energy. And we put an A here to say that this is really just our activation energy. And the activation energy is actually defined as being the minimum amount of energy required to get a chemical reaction to take place. So the minimum amount of energy. So what I'm going to do is I'm going to go over here. I'm going to take a look at this golfer over here. So you have this female golfer. She's trying to get her golf ball to get over top of that hill and, of course, get over into that cup over here. One of the things that I know is I know that if she was to take and hit the ball with maybe enough force to go right here, then what's going to happen is the ball's going to just come right back down towards her in this case. If she hits it with a little bit more force, hey, it's coming right back down. It's not until she hits it with some minimum amount of force to get that ball to where it can now transition over the hill and over to the other side. And keep in mind, if she hits it with a minimum amount of energy, gets over. She hits it with more energy, it's getting over. But I need that minimum amount of force in this case to get the actual ball to get to the point where it can roll down to the other side. We're going to see the same thing's going to kind of play out when we take a look at our chemical reactions. And once again, in this case of the scenario of the hill where I give it the minimum amount of energy, that's kind of indicative in this case of our activation energy. And can now go over there and reach the product side. So if we look at it, we're going to look at this thing known as an enthalpy diagram. And the enthalpy diagram is another way in which we can actually represent our thermochemical equation. We got it, hey, last night. We'll show over the heat of reaction in the equation. We'll see where we pull the change in enthalpy out of the equation. Now we got another way in which to express the exact same thing. And it's gonna look kind of like this here. Now, what I'm gonna do is I'm gonna come over here and I'm gonna kind of draw what's really going on here. We're gonna take a look at, initially, a exothermic reaction. So we're looking at an exothermic reaction. And this is going to be the enthalpy diagram for how an exothermic reaction looks. If I think about an exothermic reaction, let me think about it for a second. Energy's being released. That means, in order for that to occur, I must have my reactants, which I'm going to just write right here, my reactants. And let me point one thing out. Right here, this is my energy. So that's energy. So my reactants have some energy here. And then I would do right down here and put reactants, arrow, products. And if I think about it, if I have energy being released, will my products end up being higher or will they end up being lower in this case? Lower. They gotta be. Think about it. If I want energy to be released from this expo marker, right now it's at high potential energy. If I take the expo marker and I pluck it off of here, it's gonna fall down to lower energy. And I can say that, hey, it just lost energy in this case. So what we're gonna do is we're gonna have our products just be at some lower energy. And then all we are going to do is the following. We're going to go up here, we're going to put a little hill here just like we saw with the little golfer, and then just kind of, hey, connect those two things. Explain what's going on here. If you look at it, give me 1 second. If you look at it, one of the things that you're going to notice here is that if I want these reactants to go over to the product side, that just like we saw with the golfer, the same thing is going to play out right here. We're going to see that there's some minimum amount of energy to get up to the top of that hill. And we call this thing our activation energy. So long as I give it that amount of energy, it's now going to transition over to the product side. If I give it less than that amount of energy, it's like, nope, can't do it, still can't do it. But if you give me more, or at least that minimum, it's going over there. All right, the next thing we got to look at is we got to look at the net overall energy of the actual reactants and products. So if I look at, in this case, the actual overall energy of the reactants and products, then one of the things that I know is I could do something like this here. Delta E. And a lot of times we're going to see in a second that the delta E is also kind of referred to as our delta H. It's a form of energy in this case. But if I look at it, I know that I can say, hey, anytime I have delta, it's always going to be, in this case, energy final minus energy initial. So if I look at it, that's my final energy. That's my initial energy. Which means that when it comes to the actual change in enthalpy, the change in energy is really just the difference between the reactants and products. This is my delta H, and when I look at it, it's going to come out being some negative. I want to make sure it doesn't get lost, that line right there. It's going to be some negative value associated with it. And we take a question in 1 second. Just want to show one more thing. Also, just keep this in mind, is that there is energy that I'm going to put in right here. So going from here all the way up top of that hill, I didn't want to go over top of the blue, it's fine to go over it, I just want to make sure you can still see it, to right about right there. That energy I put in, I get right back out. That's like a wash in this case. The true difference in the energy is right here. That's the amount of energy that is ultimately being released here. Which means that one of the things that we can do, and then I'll take any questions you have right after this, is we can do things such as take our enthalpy diagram from maybe last night's homework assignment. Where's our last night's assignment? Here it goes right here. I'm going to go to an exothermic reaction. I could ask you, hey, you know what? Write the enthalpy diagram that represents this reaction right here. And if that's the case, all you're going to do is the following. Wait a second. Did I ever push record there? Yeah. Okay. Let's just say. And once again, I told this class about that time that I recorded a whole lecture. I didn't. So basically what happened, I'll tell you, let me get back to this problem. I was here. I was like, okay, you know what? I need to record a lecture for my AP class. And I can't remember why, but I had to record the lecture for him. So I came in here during the cub period. And I sat here for 45 minutes, going through the slides, explaining things, had the calculation. I go and I walk back to my phone, and I look at it, and I'm like, I can't believe this. I never hit the record, which meant, guess what I had to do all over again? The whole 45-minute lecture all over again. It was awful. You don't understand my facial expression when I got to the phone and saw that it wasn't even turned on in this case.
Was this on Tuesday?
No, this is a little while ago. I learned my lesson in this case to make sure I turn that thing on. Here we go. If you have to draw the enthalpy diagram for this thing, I'm just gonna go energy here. And I'm gonna go, instead of reactants, products, I like to just do this right here. R to P. Hey, going for reactants and products in this case. So all I'm gonna do is I'm gonna take my reactants, and where I have the line, I'm gonna place my reactants there. In this case, I've got 2 NO2 gas. And then I'm gonna go to my products, which I know are lower in energy, and I'll put them down here. So I got N2 gas plus, what is it, 2O2? Yes, 2O2 gas. And then what I'm gonna do is just, once again, kind of draw this curve. And for right now, when you draw kind of that little curvature part right here, if you make it a little bit higher, a little bit lower, it's okay. I just need to see that, hey, there is some barrier that's kind of preventing that reactant to get over to the product. So then the next thing we can do is we can go in here and label this thing. We can say, hey, you know what? Going from here all the way up to the top of that hill is my activation energy. Going from the reactants to the products will represent, in this case, my delta H. And I'm gonna go in here, I'm gonna actually say delta H is equal to, and what do we say? It's gonna be negative 67.8 kilojoules. So I'm just showing once again, hey, going from here to there, that delta H is this value right here. It conveys the exact same amount of information as this thermochemical equation. Reactants, products. The amount of energy being lost, right there. It's showing once again, that is gonna be reflective of the difference. Now, one more thing, I'm gonna take questions right after this. I just wanna show you endothermic. Endothermic reactions are easy. You're gonna go in here, we're gonna go energy, reactants, arrow, products in this case. As a matter of fact, I'm gonna show a endothermic. I'm actually gonna take one. Hey, that's endothermic right there. I'm gonna start off by just writing my reactants right here. So reactants is gonna be CH3OH gas right here. Products in this case, because it's endothermic, it's gonna be higher or lower? Higher, because it's gonna be some net increase in energy here. So I'm just gonna put the products a little bit higher here. So I'm gonna go CO gas plus 2H2 gas here. I'm gonna go up here and just once again show my little barrier right there and then kind of come down. What is my activation energy? Well, it's pretty easy. That's just going once again from the reactants all the way up to the top of that hill right there. That's my activation energy. I need that minimum amount of energy, give it more, perfect. But at least you gotta give it that amount to get it over to transition to the products. My change in enthalpy, once again, it's just going from the reactants, in this case, to the products. Delta H, in this case, is going to be equal to a positive 90.7 kilojoules. That's the net increase in this case. Easy enough, enthalpy diagram. Now, what I do is I'm going to show you an actual reaction and kind of show how that reaction is playing out within this actual enthalpy diagram. So I'm going to go right here. And we are going to this slide right here. If you look at this reaction is a really simple reaction that's taking place. We got this organic molecule, which is called methyl isonitrile. Wait until you get the organic chemistry. You gotta start looking at these actual naming, and it's a little more complicated than the nomenclature that we've learned in this case. But if you look at this actual molecule, only thing that's taking place here is we are going to have to break, in this case, this bond right here. I gotta break that thing. And when that bond breaks, I'm gonna end up producing a different molecular compound. Because right now, carbon's attached to nitrogen. We're gonna break this bond, cause this thing to flip over, and you get a carbon connected to carbon. So that's completely different. They are not the same in this case. But once again, in order to get that product over there, I must break that bond. So kind of look at it here. Once again, the minimum amount of energy required to break the bond will be the activation energy. So here we go. I got my molecule, and once again, I need to break it. The way that this bond is broken is you can kind of think of this as maybe being a spring right here between the carbon and the nitrogen. And if I start to kind of flex that spring, so I'm trying to break that spring, if I bring it up to a certain point and I let it go, that's just gonna spring right back. I didn't break the bond all the way. I can even stress that spring even more and more and more, and it's like, hey, nope, not gonna get there. It's not until I get to the top of the hill that I have now broken the spring. And now it's gonna flip over, start to reform the new bond, and go back to its stable state in this case. So the only thing we're looking at on this hill is that we just haven't met the requirement to break the bonds in order for it to, once again, transition over to the other side. So in the notes right here, you're just gonna see some things that we've already talked about. One, if we go in the actual, wait a second, right here, this is the one I want. If we look at the actual, which they show as delta E, for us, I would tell you that, hey, you know what? Change it to delta H. For us, we'll always see it as delta H. Delta H, once again, is a form. Heat is a form of energy. So it is okay to say, in this case, delta E, but we always say the change in enthalpy sits right here. So once again, it tells you right down there, it says, hey, the change in enthalpy is really just a difference in the energy of the reactants and the products. It's as simple as that. All right, next thing that we gotta look at. As we said already, that if we have a exothermic reaction, if I flip that reaction around, it becomes what? It becomes endothermic. So this next one makes sense. It simply says that, hey, if we look at going in the forward direction, the forward direction of this reaction says, hey, I am exothermic. That's right, because the reactants are lower in energy. But at the same time, if I wanted this reaction to go in the reverse direction, then this would be my reactants. And if you look at it, now my products are actually at higher in energy. So it does show that the opposite direction is going to be opposite. Look here. You are endothermic. Hey, opposite. You're now exothermic in this case. This slide has something new on it. It simply says, and I've been saying it, I keep on saying, hey, you know what? It goes up here and kind of transitions over to the other side. And I intentionally been saying that because that's actually called the transition state. It's the state at which the bond is kind of being broken, and also the bond is going to start forming itself. So it's just called the transition state. So that peak right there. This thing right here, where the bond is like broken, completely broken, and it's starting to reform itself, it's called an activated complex. So the actual molecule, when it's broken apart at the very top, most unstable place, activated complex, nobody wants to be at high potential energy. It's like, I don't want to exist here, so it just really quickly goes over to the side. It has that lower potential energy over there. Once again, we said that we have our activation energy. Sometimes I refer to this thing as my activation energy barrier because it's like a barrier that prevents the reactants from getting over there to the product side. The next slide. All the slide shows is what we've already got up here on the board. It just simply says, hey, if you have endothermic, it goes higher in energy. Hey, if we go exothermic, it comes down lower in energy in this case. I just want to give you two pictures to kind of show you the difference between the two. The next slide, I'm going to skip over because I want to make sure that we make it. Wait a second. I have a quick question for you. What if I had the following? Say I have another reaction. I'm going to draw kind of this enthalpy diagram right here. It's also going to be exothermic. So this is going to be exothermic as well. See if you can figure this out. I think you can because I believe in you. I'm going to say, you know what? Maybe they start at the exact same amount of energy for the reactants and products. And it does something like that there. And let's say this is reaction A. And this happens to be reaction B. Which reaction is going to end up being the slowest? B. Because one of the things that we're going to see is that for A is going to say, hey, once I get here, I get to start producing those products. Look at me produce it. For B, it's going to say, hey, you know what? No, still not enough. I still can't go anywhere. I still can't go anywhere. I still can't go anywhere. And this thing is like constantly just continuously producing more and more of the products. So one of the things you're going to see, not this one, we'll skip over this, we'll have a chance to do something like this when we look at tonight's homework assignment. You're going to notice that the smaller the barrier, the faster it's going to proceed. I mean, it's just logical. Hey, you're really slow, you're going to end up being fast. Which brings us now to this thing known as a catalyst. A catalyst does what to a reaction? It speeds it up. But look at it. We can easily explain in this case what a catalyst actually does. If you look at the picture, I show you two activation energies. I have this blue curve, and it says, hey, the blue curve is the uncatalyzed reaction. And then the next thing we got is we got this red curve down here. And the red curve says, hey, I am the catalyzed reaction. Adding the catalyst lowers the activation energy barrier, which means that, yes, the reaction is going to proceed faster. One thing I want to point out, if I ask you to go in and draw, so maybe I give you the uncatalyzed reaction, and I said, hey, you know what? On this thing, I want you to write the catalyzed reaction. What you will not do, matter of fact, I'll put it in red to emphasize that this is not what you're going to do here. You don't do something like, first of all, oh man, I don't think I can't wait till we have a faculty student basketball game. All right, so here we go. We're going to go here and go like that. That's bad. That's really bad. Because if you look at it, what does that really tell me? It says, hey, the uncatalyzed reactants, they had like some high energy. And then all of a sudden the reactant said, hey, you know what? You had a catalyst. I'm something with low. No, it is the same amount of energy, whether you add the actual catalyst or not. The reactants are the reactants. It's almost like me saying, hey, here goes the expo marker. It has a choice versus this expo marker right here. One is going to simply, both are the same potential energy because they're both the same expo markers. That's just one expo marker is going to be like, hey, I'm going to go, in this case, really high. This one, I'm just going to go really terrible. You can't show it there. But only thing I need you to do is that if I ask you to draw it, just start off at the exact same point, end at the exact same point, and then just once again, I don't care how you draw the curve, just make sure the curve is lower than the thing that's uncatalyzed. So start at the beginning and end at the end, because it's still the same reactants and it's still the same products that we're starting off with. All right, any questions here? All right. And now we have time to show it to you. Next thing we're going to talk about is we're going to talk about this thing known as the collision model. And the collision model is really easy. It says, hey, if you want to have a chemical reaction take place, guess what you have to have? Collision. So let's watch this. I'm going to show you a FET video here. Here. Where is the FET video? Do I have it up? I don't. So we go here. Collision. Nope. Chemical kinetics. That's what I want. All right. So let me explain what's going on here. I'm going to see if this class says something different than my other class. And you'll see the question in 1 second. All right. So, quick question for you. This is what color?
White.
Whoa, 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 whoa. I know my eyes are bad. Let's try this again.
Oh, it's yellow.
Oh, okay. I knew you were going to say it. That's yellow, right? What color is this?
Red.
Dude, that's
Red. It's like maroon.
It's pink.
Or like not maroon. It's like rose.
Can I zoom in? Let me see if I can zoom
The
in
other
here.
one's red. So that means pink. That's pink. Oh, wait,
That's pink?
yeah.
You know there's more fuchsia?
It's pink.
It's magenta.
magenta.
Yeah, it's
It's
magenta.
in the pink family that it is in the red family.
Okay. I'm going to always defer in this case to young ladies since men are slightly more colorblind than females in this case. So if you say it's pink, I'm going to go with pink in this case.
What do you think it is?
I think it doesn't look, like when I think of pink, I think about a little bit
I feel like it's
of a lighter, I don't know, maybe I'm thinking fuchsia
Pink
or
is a
something.
family. Pink is not one color.
Okay. I do agree, that is fact. Right. Give me 1 second, I need to make sure this is showing at 100%. And here we go, and reset it. Show correctly. Perfect. All right, so let me show you what's going on here. Basically what you're noticing is I have a pink down here. And it's simply saying that, hey, this pink needs to hit that, this yellow. Jedi mind trick. This yellow needs to actually hit this pink. And when the yellow hits the pink, these two will go together, and the purple is going to catch, not the purple, but the gray is going to end up flying off in this case. So I need the pink, the yellow and the pink to collide with each other. Gray comes off. Which means that if you look at it, I start with one thing, hit something, and one flies off. This reminds me of a certain reaction that we saw in the first semester, which was going to be what? Single displacement reaction. Now, watch what's going to happen here. I'm going to come and take this plunger. I'm going to pull the plunger back just a little bit. I'm going to let it go. And what you're going to notice is I did not get a chemical reaction taking place here. Remember, chemical reaction implies that I got to have something new. There's nothing new there. So what it is, I'm going to go back here, I'm going to restart it all. And this time I'm going to pull the plunger back a little bit further. And yeah, still nothing in this case. Which means that technically, guess what? I have not met the what?
Like the activity series.
Not the activity series, but the activation energy. But the activity series does go along with the single displacement. But I did not meet the activation energy, the minimum amount of energy required to break the bonds. How I'm going to break these bonds? By going with a more forceful collision. And if I can have a hard enough collision, then the bonds are going to break themselves. I'm going to end up ultimately, hopefully, getting that product here. So what I'm going to do, for the sake of time, I'm going to pull this thing back even further, far enough that I know that it's going to take place here. And what you'll notice is that I made sure that I hit it with enough energy in order for the bonds to break. And then I ended up once again with the actual products. So the only thing the collision model simply states is it states that in order to have, in this case, chemical reactions take place, we gotta have molecules, in this case, colliding. Now, one of the things that we just saw is we saw that, hey, not every collision is gonna lead us to the actual products. But instead, what I need is I gotta at least have a collision that has the minimum amount of energy, that activation energy. So that's one criteria. The other criteria is that I need, if I go back to the simulation here, so go right back here really quickly so you can see it, restart it. I need this yellow to hit the pink in this case. If I kind of rotate this molecule 180 degrees around, and if the yellow hit the gray, there's going to be no reaction. This reaction says you must hit this right here. So yellow must hit pink. So one of the things that we're going to see is that the molecules do have to have collisions. Got to have that activation energy. But also what they're going to be required to have is they gotta have what is called the correct orientation upon the collisions. So right here, we have what are called effective collisions. These are what we want. We want effective collisions because these are gonna produce the products. In order to have an effective collision, you gotta have correct molecular orientation upon collision. I'll show you this one in a second. The other one, hey, we kind of understand, hey, if I don't have the activation energy, then of course this thing is not going to meet that minimum amount of energy to get the bonds to actually break. And as a matter of fact, if you want to, just to, we're absolutely certain or clear here, you know, it's got to have at least the minimum. Is that thing right there, the activation energy. Give me more, it's going, but I need that minimum amount. So we're going to take a look at it. So look at this reaction right here. I'm going to look at some of the ways in which we need the orientation to be to get these products over here. So what I'm going to do is I'm going to just write the reaction up here really quickly. And the reason I'm doing this is when I go to the next slide, you're going to lose this balanced equation. And I need that so you can kind of see what is going on here. So I'm going to end up getting 2 nitrogen monoxides. And also I'm going to get a Br2. All right, watch what's going to happen here. Here goes my BRNO, so BRNO, so that's my reactant. Here goes the other one sitting right here as well. This collision, if I had this sort of side-by-side collision playing out, this, so long as I have the minimum amount of energy to break the bonds, is going to have the proper orientation. And the reason why I know it's going to be proper orientation is because I need these two bromines to come in contact with each other to get me my diatomic bromine. And what's going to happen is once they collide and the bonds are broken, they will stick together. These bonds will simply break and the two nitrogen monoxides will go off. So I need my bromines to come in contact. Even if I look at this one right here, this is still okay. My two bromines are coming in contact with each other. I get my diatomic bromine, and the two nitrogen monoxides go off. This is not okay. Because, hey, even if I hit them with enough force that the bonds do break right here, all it's going to do is just reform the bonds because it doesn't have the proper orientation. Even if you look at it, I can say something like this. It's not a proper orientation. That's not, they'll collide side by side, but that's going to be still no reaction taking place because I need the two bromines to hit. Now, keep in mind what's going to end up happening. When it comes to your homework, I'm always going to show you what the actual orientation is going to be. So it's going to look maybe like this here. I'll say, hey, you know what? Above is showing the correct orientation upon the collision. And so long as it has the activation energy and it has this orientation, then it shows me that this green needs to hit the purple here. So the fluorine has to hit, in this case, the nitrogen. And so long as that happens, the fluorine will stick to the nitrogen, and this fluorine will just go flying off. So if I look at this one down here, it says, hey, based on the reaction, what is the logical explanation for why the reaction does not occur? Well, I'm going to go in there and simply say, you know what, I can see that it's going to be what? Is the orientation of the activation energy? Oh, I see it. What is it going to be? Based upon the picture that I got there. Come on. Last class, I just say it really quick. I know this class is extremely bright. What is it going to be? It's orientation. How do you know that?
Because of like the difference in where the fluorine is.
Exactly. Who did we say the fluorine had to hit in the top one up here? The nitrogen. Hey, the fluorine are hitting the red things there. So they can't get to the thing they need to attach onto to ultimately get the actual product here. And that's why you notice that right afterwards, like they just collide and just bounce off. They don't have the right orientation. For this next slide right here, it says, hey, based upon this, let's just say that they bounce off of each other. So no reaction is taking place. What could be the logical explanation for why this one is playing out?
There's not enough energy.
That's it. They do not meet the minimum amount of energy. They have the right orientation. Right there, we said fluorine has to hit the nitrogen. Well, that's what it's doing. But if it's bouncing off, then it's like, hey, we didn't give it enough energy to break the bonds so it can actually go and produce its products in this case. Let me point out what your homework's going to look like for tonight. Tonight,